S, right, where S is a closed, oriented, connected surface of genus at least 2. Okay, and in this setting, we can consider the tightness space of S, right? And if you think about this geometrically, you can think of this as the set of hyperbolic structures, or the deformation space of hyperbolic structures. You can equip your topological surface with. Okay, but you can also think of this from a representation theoretic point of view, and then this is the set of discrete and faithful representations. From gamma to PSL2R, right, which is the group of orientation-preserving isometries of H2, consider up to PGL2R, right, which is the isometry group of H2. Okay, another piece of notation, I'm also going to let V denote an n-dimensional real vector space. Okay. So then the first fact we need is a standard fact from representation theory that tells you that there exists a unique, up to conjugation, irreducible representation, which I denote by iota, from PSL2R into PSLV. Okay, and you can think of this as some very natural way to include PSL2R into this bigger Lie group. Right, and what this gives us is a natural embedding of the tightness space of S into the space of homomorphisms from gamma to PSLV, right, consider up to conjugation by PGLV. Okay, how does this map go? Well, I take any conjugacy class in here. Okay, so I'm thinking of tightness space now here as the conjugacy classes of discrete and faithful representations. And then I pick any representative in this conjugacy class rho, and then I post-compose it with this irreducible representation here, and then I take its conjugacy class inside of here. Okay, so you can check that this is a well-defined procedure. Okay, and this brings us to our first definition. Okay, the PSLV Hitchin component, right, which I'll denote by hit V of S today, right, is the connected component of this space, which I denote by xv of S. Okay, that contains the image of I. Okay, so some examples. When the dimension of V is 2, so when n equals to 2, all right, then the Hitchin component is just the tightness space of S. Okay, so this follows from the well-known fact that the tightness space is a connected component of its character variety. And when the dimension of n is 3, right, the Hitchin component can also be identified with the deformation space of a certain kind of geometric structures called convex row projective structures, right, which Sam talked about yesterday. Convex row projective structures on S. Again, this is the work of Troy Goldman. Okay, and when n equals to 4, you can do a similar thing. Right, in that case, the Hitchin component can be thought of as the deformation space of convex foliated RP3 structures on the unit tangent bundle of the surface. Okay, and this is the work of Gisha Wienhardt. Okay, so I'm not going to explain to you what these geometric structures are, but the point is that at least in the case of when the dimension of V is small, you can see that the Hitchin representations all have very good geometric properties, right? They all arise as holonomies of certain kinds of geometric structures. Okay, but what can you say about the Hitchin components in general? Well, the first to result in that direction is the theorem of Nigel Hitchin, who proved using Higgs bundle techniques, right, that the Hitchin component is real analytically diffeomorphic right, to a cell of dimension n squared minus 1 times 2g minus 2, right, to r to the n squared minus 1 times 2g minus 2. Okay, so this space, the global topology is trivial, and you can say what its dimension is, okay? Unfortunately, Hitchin's techniques did not tell us much about the geometry of the individual representations in the Hitchin component, which is kind of a pity, right? Because at least in the low dimensional cases, you see they have a lot of good geometric properties. Okay, and that was a problem until Labourie came along, and he proved that every PSLV Hitchin representation is the Nosov. Okay, and we saw this notion a little bit yesterday in Ferny's talk, and it basically says that every PSLV Hitchin representation has good geometric properties, right? In particular, they are all quasi-isometric embeddings of all these representations are quasi-isometric embeddings from gamma equipped with its word metric into PSLV equipped with any left invariant Riemannian metric. Okay, so this is roughly saying, informally saying that the way the representation takes gamma and puts it inside of PSLV does not distort the intrinsic geometry of the group too much. Okay, so there we have it, right? This is the Hitchin component, right? It's a component of the character variety that consists only of smooth points of the character variety. That's where the real analytic structure is coming from. And every representation there has good geometric properties. Okay? So next, I'm going to introduce talk about the second object, which is the Goldman symplectic form. Okay, and this is a symplectic form that you can define in a pretty general setting, right, on the set of smooth points of a character variety from a surface group into any reductive Lie group. But for today, I'm just going to talk about this in the setting of the Hitchin component. Okay, and to define this, you need to use, well, it was Goldman who defined this, at least the way I'm writing it. And you need to use some observations that he made. Okay, the first is that if you look at the tangent space to the Hitchin component, and any conjugacy class in here, okay, and if you pick a representation in this conjugacy class, then this gives you a canonical identification of this tangent space with the first cohomology of a surface with coefficients in this SLV bundle over the surface twisted by at composed with rho. Okay, and then once you have this, then you can consider the bilinear form B from SLV square to R, right, where you take a pair of elements in SLV and you send it to the trace of the product. Okay, so I forgot to mention, SLV here is the Lie algebra of PSLV, and you can think of this as the vector space of traceless endomorphisms from V to itself. Okay, so here I'm just taking any pair of traceless endomorphisms, composing them and taking the trace of that new endomorphism. Okay, so it turns out that this is a bilinear pairing that's symmetric, non-degenerate, and also invariant under the adjoint action, invariant under conjugation. Okay, so using this, you can define another bilinear pairing, but now on the level of cohomology. Okay. Okay, and how does this go? Well, first you send this pair of cohomology classes, first cohomology classes, to the second cohomology of your surface with coefficients in R. Okay, and the way you do it is you use the cup product to pair your two first cohomology classes to get a second cohomology class, and then you use your bilinear pairing B to pair the coefficients to get something in R. Okay, so I'll write this as the cup product and with B. Okay, and then you take the cap product with the fundamental class of your surface. Okay, so S here was closed and oriented, so you can do this, and then you get something in R. Okay, and what Goldman says is that this guy here, omega, is a symplectic form. On the Hitchin component. Okay, meaning it's that it's a non-degenerate, anti-symmetric, skew-symmetric pairing. And if you view it as a two-form on the Hitchin component by doing this at every tangent space, then this is a closed two-form. Okay? So in the case when the dimension of V is 2, okay, then the omega is the Weil-Petersson symplectic form. On the Tengren space, right? This was also proven by Goldman in the paper when he introduced this. Okay, so the question that I would like to address today is what does this symplectic form omega look like on the Hitchin component? Oh, sorry about that. Okay, let's try this one. Oh, this one, maybe. Okay, so there are a few answers, possible answers you can give here. And the first one is kind of, it's not much better. It's following the work of Scott Wolpert, okay, who studied the Weil-Petersson symplectic form in the case of Tengren space when the dimension of V is 2. Okay, so this is what Wolpert says. Okay, suppose that the dimension of V is 2. So suppose that n equals to 2. Right, then the Fenton-Nielsen coordinates on the Tengren space, right, is a global double coordinate system. Okay, so what does this mean? Well, first you need to know what are the Fenton-Nielsen coordinates, right? And basically what you do is you choose a Pence decomposition on your surface. And whenever you do that, then you can define this natural coordinate system of Tengren space, where you assign to each closed curve in your Pence decomposition a length function and a twist function. Okay, and those are real analytic functions on your surface. And being a global double coordinate system means that you can write your symplectic form as the sum from I equals to 1 to 3g minus 3 of dLi wedge d theta I, right? Where Li is the length function you assign to the ith simple closed curve, and theta I is the ith twist function. Okay, so this is kind of saying what the symplectic form looks like in this case. Since then, there's also more work in this direction. Okay, so yeah, I should go to the next board. Any questions? Okay, so when the dimension of V is 3, okay, there was a student of Bill, Hong Chan Kim, right, who also computed. He showed that the Goldman parametrization of the deformation space of convex row projective structures gives you a Dabu basis. Okay, and in the case when n equals to 4, there's also some very recent work by Hong-Taek Zhong, right, and they show kind of similar results. Okay, and the main tool they use to prove this is this procedure called Fox calculus. Okay, and which allows you to compute the Poisson pairing between certain types of functions on these deformation spaces. Okay, and the one drawback with this technique, though, is as the dimension of V gets big, the computation gets more and more complicated. Okay, and so for instance, in the case where n equals to 5, right, it's not known. Nobody has found a way to use this technique to produce a result like Scott Wolpert's. Okay, so that's one answer, partial answer. Another answer to the question, what does the Goldman symplectic form look like on the Hitchin component, kind of follows along the lines of the thesis work of Sinye, right, who says the following. Okay, so I'm going to let S prime inside of S be an incompressible subsurface. Okay, and then you can consider the Hitchin component of this subsurface. Okay, so here S prime has boundary, so I have not actually defined this for you, okay, but you can make sense of this. I guess you can look at the paper of Labourie-McShane to see how to define this. Okay, it turns out that when you look at the Hitchin component of S prime, this naturally arises as a symplectic quotient of the Hitchin component of S. Okay, so the Goldman symplectic form here induces a natural Poisson structure here. Okay, and what Sin says is that if you look at the Goldman Poisson structure here, and you compare that to the Fort-Gontran Poisson structure, right, they agree on this space. Okay, so what is the Fort-Gontran Poisson structure? I'm not going to really define it, but basically this space here, you can view this as an open subset of what is known as the Fort-Gontran X moduli space. And there, Fort-Gontran define a Poisson structure using some cluster variables. Okay, so if you come from the world of cluster algebras and cluster mutations, then this is a possible answer to the question. Right? It relates the Goldman symplectic structure, right, to the Fort-Gontran Poisson structure if you're willing to take subsurfaces. Okay? And I should mention maybe 3, that there's also some related work by Martin Bridgman and François Labourie, where they compute the Goldman-Poisson pairing between certain kinds of functions on the Hitchin component, right, like length functions and trace functions. Okay. So I guess that's kind of a brief overview of what we know about the Goldman symplectic form, the Hitchin component. Okay, so now I'm going to move on to state our main results. Okay, so it's part 3 of the talk. Okay, and so the goal of this project is to I guess the goal of this talk maybe is I would like to explain to you a new way to think about the Goldman symplectic form. Okay, and our approach to this problem it's quite similar. It's similar in flavor to the work of Bonahon-Sauzen in the case when the dimension of V is 2. Okay, but what we do is actually much more concrete. Okay, so to describe my main results, first I would like to tell you about what is an ideal triangulation and what is a bridge system. Okay, some topological choices I need to make on my surface. Okay, so let T be an ideal triangulation. On S. Okay, and J a compatible bridge system. Okay, so what are these things? Okay, let me move here. So these are actually topological objects that you can associate to your surface. Okay, you can define them purely using the topology of your group. Okay, but if you choose a hyperbolic metric on your surface, right, then these objects become realized as hyperbolic as geometric objects on your surface. Okay, and so I'm going to tell you what is the geometric realization, because this is a little bit easier to explain. Okay, so I'm going to choose hyperbolic metric. Sigma on S. Okay, so sigma is S equipped with your hyperbolic metric. Okay, and so here's my surface. Sigma. Okay, and what is an ideal triangulation? An ideal triangulation is a finite collection of simple geodesics that cut your surface into hyperbolic ideal triangles. Okay, so if you do that on your closed surface, you necessarily have to use some closed geodesics, say this one and this one. Okay, and what you do is from here, you keep adding in simple geodesics. They are not closed. They kind of spiral towards these guys. Okay, so maybe a picture can look something like this. Okay, on this side, and on this side, you kind of spiraling like this. Okay, and now we're going to call these guys the isolated edges of your ideal triangulation. And the red things will be called the closed edges. Okay, and if you look in the universal cover, what you're going to see is the following. Okay, you're going to see lifts of these closed edges. Okay, there are going to be infinitely many of them. I'm just going to draw two. Okay, so this is the picture of sigma tilde, right, which is isometric to the upper half plane, or the Poincare disk. And then, let's see, where's my orange? You're going to see these lifts of the isolated edges that kind of accumulate, right, onto your closed edges, the lifts of the closed edges. So it looks something like this. Okay, on this side, you have the same kind of picture. Okay, and so on, and so on. Okay, so this is what your ideal triangulation sort of looks like in the universal cover. Okay, so what about a bridge system? A bridge system, if you choose a hyperbolic metric on S, then a bridge system is simply, can be realized geometrically as a short transverse arc across each closed edge. Okay, and what this does in the universal cover is that it picks out a pair of triangles across each closed edge, right? So that each of them shares a common vertex with the closed edge. Okay, and you do this in a gamma invariant way. Okay, so it looks something like this. Okay? So this is some topological data I chose on my surface that, if I take a hyperbolic metric, then it gets realized as something geometric. Any questions? Okay. So with this, we can state the first theorem. Okay, which is that if you choose T and J, right? So ideal triangulation and a compatible bridge system, then this determines a symplectic trivialization of the Hitchin component. Okay, so in other words, there exists a symplectic vector space which I'm going to denote by WTJ. Okay, and a symplectic bundle isomorphism denoted by phi Tj. Okay, from the tangent bundle, I guess this should be the tangent bundle. Okay, from the tangent bundle of the Hitchin component to the product of the Hitchin component and this symplectic vector space WTJ. Okay, and both of these are viewed as bundles, vector bundles over the Hitchin component. Okay, so this is a bundle isomorphism so that when you restrict to the fibers, right, it's a symplectic isomorphism. Okay? So once you have this notion, then you can make the following definition. Okay, and Tj parallel vector field okay, on the Hitchin component is a vector field, is 1, okay, that is parallel with respect to the flat connection induced by your symplectic trivialization phi tj. Okay, so once you have this trivialization of the bundle, right, then it induces a flat connection on the bundle, and it makes sense to talk about the parallel sections to this flat connection, and that is what these tj parallel vector fields are. Okay? And now we can state a second theorem. And it says the following, if x1 and x2 are tj parallel vector fields, okay, then when you take the Lie bracket of these two vector fields, you get a 0 vector field. Okay, so in other words, if you, okay, so I should emphasize that here, these two vector fields are parallel with respect to the same tj. Okay, if you change your t and j, the notion of parallelism changes. Okay, but if you use the same tj, then this is saying that if you look at the integral flows of these two vector fields, then they commute as flows. Okay? So I should point out that maybe this is a little bit of an understatement of what we do, because when we say determine here, right, this is completely explicit. Okay, and so you can actually use this to perform computations. Okay, and here this theorem is also an understatement of what we have, right? In fact, well, I'll talk about it later in the proof. Okay, but once you have these two theorems, then you can have, there's a bunch of corollaries that follow almost immediately. So first, every tj parallel vector field is Hamiltonian. Okay, so this gives you a huge collection of examples of Hamiltonian vector fields on the Hitchin component. Also using this, well, we can show that the Hitchin component equipped with the Goldman symplectic form, right, is a complete integrable system. Right, so you can find a half-dimensional family of functions that Poisson commute. Okay, and we can also use this to produce explicit examples of Lagrangian submanifolds. Of the Hitchin component. Okay, I don't think this was known before. We can also use this to give a new proof of a Senior's result. Right, to show that the Goldman symplectic form and the Goldman Poisson structure on subsurfaces agree with the foregone trough one. Okay, and our proof here is much more concrete. Okay, it's basically a computation, right, as compared to Niels' proof, which you use much more abstract arguments. Okay, and finally, if we choose our ideal triangulation to be of a particular form, okay, so if T satisfies the following, okay, I'm going to just draw a picture. Okay, so, well, okay, first, the closed edges of T, the closed edges of T give a Pence decomposition. Okay, so I choose T so that I have as many closed edges as possible. Okay, that's the first point. And the second is what does your triangulation look like on each pair of Pence given by your Pence decomposition? It looks like this. Okay, so let's say this is a pair of Pence given by my Pence decomposition. And then if you look at T restricted to this pair of Pence, right, is going to cut this pair of pens into two ideal triangles using 3 geodesics that kind of spiral between the closed edges. Okay, so one that kind of looks like this on this side. Okay, and then you have one more that goes from here to here, and one more that goes from here to here. Okay, but I'm not going to draw them in. Okay, so if you choose your ideal triangulation to be of this form, right, then the symplectic trivialization phi tj gives an explicit global double coordinate system. So give explicit global double coordinates for the Hitchin component. Okay, and when you restrict this to the case when the dimension of V is 2, okay, this recovers the Fenton-Nielsen coordinates. So this recovers the Wolpert formula. Okay. Sort of, roughly, but I'll explain this in more detail later. Okay, and yeah, so I mean, this is kind of a testament to our techniques, right? That I mean, behind this all of these theorems, right, is a procedure to explicitly compute what the Goldman symplectic pairing is. If you give us the two vector fields the two vectors you want to compute, right, in a certain form. Okay, and kind of theorem 1 and theorem 2 is saying that this procedure is kind of useful if you want to prove kind of abstract theorems, but you can also actually implement this procedure to produce explicit functions, okay, these double coordinate functions, okay. So in the remaining time, I would like to explain kind of maybe the main computational tool that we introduce to compute the Goldman symplectic form. Yes? Yeah, so maybe more, yeah, I should have been more explicit. What I mean is I can produce n squared minus 1 times 2g minus 2 functions, okay, so that you can write the Goldman symplectic form as the sum of dl wedge df wedge dg. Yeah.
But these functions, they are local differomorphism.
Globally defined functions. So this is a global, it's a global coordinate system. They define the symplectic form globally, just like the Wolpert formula.
Right, but they define the mapping of that to R,
Yes, yes.
Globally differomorphism.
Globally diffeomorphism.
So they match everything. So it's really.
Yeah. So this gives. So if you look at the image of this coordinate system, yeah, you get an open set inside of R to the n squared minus 1 times 2g minus 2. Right, I mean, but just like like even for Fenton-Nielsen coordinates, right, your length functions always must be positive, right? So it's the same kind of thing, right? You get a half space, right? Cut out is, basically your length functions must be positive, right? That's why you don't get the full R to the n squared minus 1 times 2g minus 2. Okay. Yeah. So that means that yeah. Okay. So you get, so this is saying that the Hitchin component, right? If you think of this as a symplectic manifold, this is quite easy, right? It's basically an open set in some Rn. Yes? No, explicit. No, explicit. No, but easier, as in like Fenton-Nielsen coordinates. It's actually a coordinate system. Yeah, no linear relations between the functions. Okay, so at least I would like to try to describe the proof in some broad strokes. Okay, but let me mention that the main, the point of view we're taking, it relies on this theorem of François Laborie and Olivier Guichard, okay, who says the following, okay, if you look at the Hitchin component, this is canonically in bijection, right, with the space of Ferny curves, C, from the boundary of gamma into the space of complete flags, right, that are rho equivariant with respect to some rho from gamma to some rho from gamma to PSLV. Okay, consider up to projective transformations. Okay, you can think of this as a subset of the space of Ferny curves. From the circle to the space of flags. Okay, so what is FV? We saw that in the previous talk already. This was the space of full flags, as Francois calls it. And it's basically a full flag is a nested sequence of subspaces of V, one of each dimension. Okay, and so this curve assigns to every point in the circle, right, a flag. And the Ferny property here, I'm not going to be precise, but you should think of this as telling you that this curve has maximal transversality properties and also have some strong continuity properties. Okay? And so what is this? Well, here my group, remember gamma was the fundamental group of my surface. Okay, and this is known to be a hyperbolic group. And the boundary of gamma here is I'm taking the Gromov boundary. Okay, and this is topologically a circle. So it makes sense to say when a map from this circle into FV is Ferny. Okay, and also you have a natural gamma action on the boundary of gamma, and you have a PSLV action on the space of flags. Okay, so it makes sense to require this to be equivariant with respect to some representation. Okay, and so this space, sometimes I'll refer to this as the Hitchin locus inside of the space of Ferny curves. Okay, and so what this theorem is saying is that instead of thinking of the Hitchin component as a space of representations, okay, I'm going to think of it as a space of Ferny curves satisfying some equivariance property. Okay, and this is kind of the point of view that we'll be taking. Okay, so the main computational tool we introduced to compute the Goldman symplectic form is this thing we call an admissible labeling on a barrier system. Okay, so I would like to explain to you what this is. It's a little bit technical, but you should bear with it, and hopefully we'll see the results, kind of the fruits of our labor. Okay, so well, what is a barrier system? Okay, I'm going to start by choosing an ideal triangulation, T on S. Okay, and I'm also going to choose an orientation on T. Okay, so an orientation on T is just a choice of orientation on each of the ideal edges in T. Okay, then I'm going to let B, right, be defined to be T union the set of non-edge barriers. Okay, and this thing together is called a barrier system. Okay, so just like the ideal triangulation on the surface, this is something that's purely topological. But if you choose a hyperbolic metric on your surface, then these things become realized as geometric objects on your surface. Okay, and again, I'm going to tell you what these non-edge barriers are by describing what their geometric realization is if you choose a hyperbolic metric on the surface. Okay, so choose sigma. Okay, then what we had previously, right, was since we've already chosen our ideal triangulation, right, our surface is now cut into a bunch of ideal triangles, okay, that look like this. Okay, so this is one ideal triangle. And this is inside of sigma, right? So it's actually a hyperbolic ideal triangle. Okay, and what you do is you look at the barycenter of this ideal triangle, and then you draw 3 geodesic rays kind of going off to the vertices of this triangle. Okay, and then you orient them this way. Okay, my triangulation was oriented as well, right? Okay, in some gamma, in some invariant way. And so each of these guys is called a non-edge barrier. Okay, so these are basically the barriers in B that are not edges of the ideal triangulation. Okay, so that's that. Okay, so next I need to describe to you some very special endomorphisms on the Lie algebra in SLV. Okay, so let F, G, and H be complete flags Okay, so that Fi plus Gj plus Hk is all of V for any ijk running from 0 to n minus 1, and I plus j plus k equals to n. Okay, so I'm choosing a triple of flags. Okay, so what does this notation mean? So remember, let's say you look at the flag F, right? This is a nested sequence of subspaces. So Fi is just the I-dimensional piece of this flag. So this is an element in the ith Grassmannian of V. Okay, so I'm choosing I want to take 3 flags with the property that no matter which combination of subspaces you use, they are always transverse. Okay, they always give you V. Okay, and then once you have this, you can define this special endomorphism, which I'm going to denote by A of ijk fgh inside of SLV. Okay, and define it in the following way. Okay, so this is an endomorphism, so I want to describe what it does on subspaces. Now, if you look at A of ijk fgh restricted to the I-dimensional piece of the flag F, this is just n minus I over n times the identity on this subspace. Okay, and if you take A of ijk fgh and you restrict it to Gj plus Hk, okay, this is going to be negative I over n times the identity of Gj plus Hk. Okay, so in other words, this is the endomorphism defined so that it has a Fi and Gj plus Hk as eigenspaces, and the eigenvalues corresponding to these subspaces, these eigenspaces are n minus I over n and negative I over n. Okay, you can check that this is a traceless endomorphism. Okay? Then using this, we can define this thing we call an admissible labeling. So definition, let rho from gamma to PSLV be Hitchin. And C from the boundary of gamma to the space of flags be the rho equivalent Ferny curve. Okay. Then I call an at rho equivariant map L from the barrier system to SLV. Okay, I call this guy an admissible labeling. Okay, if the following properties hold. First, if you look at an edge in the ideal triangulation, okay, then this guy has 2 endpoints in its visual boundary. I call it x and y. Okay, so the picture you have is, maybe I'll just draw it here. Okay, so you have an edge, E. It can be closed, it can be isolated, I don't care. Okay, and you have 2 endpoints here, right, x and y in the visual boundary, in the Gromov boundary of gamma. Okay, the labeling L assigns to this edge E the Lie algebra element, which is the sum from I equals to 1 to n minus I of some real numbers, I, n minus I, x, y, L, times A to the I, n minus I, Cx, Cy. Okay, where these are real numbers. Okay, so it assigns to this edge a linear combination of endomorphisms, these special endomorphisms, where the flags f and g come from the Ferny curve. Okay, so the Ferny property of the curve ensures that this is well defined. Okay, you got a correct transversality. Now, next, if you take any triple of barriers, non-edge barriers, B1, B2, B3, in the same ideal triangle, okay, oriented clockwise. Okay, so in this picture, my 3 non-edge barriers are B1, B2, B3, oriented clockwise. Okay, and then I'm going to call the vertices x1, x2, and x3. Okay? So when you have something like this, then you can look at then when you evaluate the labeling on one of these barriers, Bj, okay, what you get is the sum over a huge thing. Okay, you look at all possible integers, positive integers, I1 plus I1, I2, I3 in Z plus, such that I1 plus I2 plus I3 equals to n. Okay, and you're going to put in some linear combination of matrices of that form again. Okay, so these are called A, Ij, Ij plus 1, Ij minus 1, Xj, Xj plus 1, Xj minus 1, L, okay, times A of Ij, Ij plus 1, Ij minus 1, of C of Xj, C of Xj plus 1, and C of Xj minus 1. Okay, so it's kind of similar to what we did here, except now I use a triple of flags instead of a pair. Sorry, I forgot to mention. Okay, what does this mean, right? So if you have a of I, j, k, f, g, h here, and suppose that like let's say j is 0, okay, then there's no dependence on g. I'll drop the notation from this guy. So maybe I can, this guy here is the same thing as a of I n minus I 0 of cx, cy, and anything you put here, right? Because there's no dependence on g. Okay? Any questions about this definition? Sorry, n minus 1. Yeah, thanks. Okay? Mm-hmm. Right. Sorry. So yeah. So here I'm doing everything in the universal cover. Thank you. Right. So this is really you take an edge in the universal cover and you do this, and you take a barrier in the universal cover and you do this. Okay. Yeah. This is what you can choose. So these matrices are determined by your representation, and these real numbers, right, are what you can choose. Okay. And you immediately have add row equivariance because okay, well, as long as the add row equivariance is some condition on the coefficients. Okay. So what am I doing here, right? I'm basically looking at my barrier system, and I'm labeling each of the barriers, right, with a Lie algebra element subject to some conditions. Okay. So I'm going to call the set of all these guys, the AI, okay, so sorry, here there are some more conditions regarding the triple of barriers, okay? So you require that A of ijk, xyz of L to be equals to A of j, k, I, yzx, L for any ijk, xyz where this makes sense. Okay, so I require this symmetry among the coefficients of the labeling on the barriers, the non-edge barriers. Okay, so such that. Okay, and then I'm going to call A of I n minus I xy, and the set of all A of I j k xyz. Right? These all depend on L. Okay, I'm going to call this set the coefficients of the admissible labeling L. Okay, so this definition is not finished yet. There's one last condition I need to impose. Okay, but I'm going to be vague about this. So you have some linear conditions, right, associated to each closed edge of T. Okay, and these are linear conditions in the coefficients. Okay. And if you interpret this the correct way, these are basically the Bonner-Horn-Dreyer closed-leaf equalities. Okay, so these linear conditions come from somewhere. Okay, so this is what an admissible labeling is, right? I've labeled, yes?
Yeah, the number elements that you put on the no edge barrier, are those no Pokemon?
No, those are, no, they are not. They have, they look like this, right? So they have eigenvalues n minus I over n and negative I over n, right? I mean, basically, okay, so maybe where do these matrices come from? Where do these endomorphisms come from? Well, it's a long story, but basically this is telling you infinitesimally, if I want to shear, what can I possibly do? And these matrices are telling me infinitesimally when I want to deform a triple of flex, what you can do, okay? But you know, you do this in this formalism. Well, we will see what's happening next. Okay, so we have this, so now we can do the proof. Okay, so the first step of the proof is to relate this formal stuff, right, with the Goldman symplectic form. Yes?
So the leveling can you have two separate equations?
No, it cannot. Okay, so yeah, so good point. These guys, if you fix x1, x2, x3, these guys are linearly independent, these endomorphisms. So the coefficients determine the labeling and vice versa. Okay? Any other questions? Okay, so the step one is to build a co-cycle from this data. Okay, so you need to make some more choices. So I need to choose a bridge system, J, that's compatible with my ideal triangulation. And then I choose a negatively curved metric on my surface, sigma. Okay, and from this, I'm going to build a co-cycle, which I denote by mu L. So this is a co-cycle for the first cohomology of my surface with values in SLV at rho. Okay, for any admissible labeling L in A rho. Okay, so this A rho here, which depends on the ideal triangulation and the orientation, right, is my notation for the vector space of admissible labelings. Okay, so yeah, so maybe I should point that out as well. The space of admissible labelings is the vector space, right? Because the conditions I impose on the endomorphisms are linear, right? On the coefficients are linear. Okay, and another thing is I chose an orientation on my triangulation. Where is this showing up? So this orientation is showing up in this thing that I'm hiding. Okay, these linear conditions I impose, they depend on the orientation of my ideal triangulation. Okay. So how do I build a co-cycle from this data? The idea is kind of simple, but in practice, I mean, there's some technical difficulties you need to overcome. Okay, so I've chosen a hyperbolic metric on my surface, and I'm looking at the universal cover. Okay, and there I've realized my ideal triangulations and my bridge systems as ideal triangles, hyperbolic ideal triangles on my surface. Okay, and these guys are oriented, right, in a gamma invariant way. Okay, and inside each of these triangles, I have a bridge system, I have my non-edge barriers, which I'm thinking of as geodesic rays going off to infinity. Okay, so they have a natural orientation as well, right, going out like this. Okay, and now suppose I have a one simplex in my surface. Okay, how do I assign a Lie algebra element to this? Well, I look at the algebraic intersection number of this one simplex with all the barriers, and then I sum up the labeling on all the barriers, right, with respect to multiplied by the sign of the algebraic intersection number. Okay, so you do this. Now this is fine in this picture, okay, but if your one simplex crosses a closed edge, then you have a big problem because now you intersect infinitely many of these edges, and then in general, these if you take the infinite sum, it does not converge in any reasonable sense, okay? But that's where the bridge system comes in, okay? You need to choose the bridge system to make sense of this infinite sum, okay? But you can do that, and it turns out that this gives you a co-cycle, or you can define in a way that gives you a co-cycle, okay? So now you have this co-cycle, and then what do? Well, step 2. Okay, yeah. No, so the bridge system is basically telling you, okay, if my one simplex want to cross a closed edge, how am I supposed to cross it? It assigns, when you're given the choice, it tells you what Lie algebra element to put there. So the basic idea is you take your one simplex, you homotope it so that whenever you cross a closed edge, you must go along a bridge. And in between the bridges, I don't care. It doesn't matter. And then every time you cross the closed edge, you know exactly what you do. And in between the closed edge, you only intersect finitely many of these things, and so you can make things make sense. Okay? And the second step is you need to show, right, that the linear map, I'm going to denote phi rho, from the space of admissible labelings to the tangent space to the Hitchin component. Okay, where you take L and you send it to the cohomology class of mu L, you need to show that this is a linear isomorphism. Okay, and this is like kind of where the geometry comes in, right? You need to relate these formal objects to, like deformations of the Ferny curve. Ooh, I'm out of time. Okay, so maybe I should finish up quickly. Okay, but now I'm in business, right? Because now this is saying that if I take any tangent vector right here, I can find a co-cycle in that cohomology class that comes from this admissible labeling picture. Okay? So to compute the cut product, I can use now a simplicial cohomology, right? I choose a triangulation on my surface. For each edge of the triangulation, I know exactly which barriers intersect. I know which Lie algebra element I assign to it, and I just use the cut product formula. Okay, so that's what step 4 is. So maybe I should write down the theorem. Okay, so there's for any pair of admissible labelings, L1, L2 in A row. Okay, if you look at the Goldman symplectic pairing between mu L1 and mu L2, okay, this guy depends only on the coefficients. Of L1 and L2. Okay, and this property is what allows you to build your symplectic trivialization. Okay, and that's so this gives you theorem 1. Okay, and I'm out of time, so I'm just going to stop here. Thank you. Yes.
With the permanent vector fields, you said that method,
Uh-huh.
is there a reasonable expression of the function we construct?
Yes, you can. Yes. So you can compute those explicitly. In fact, that's how we get our double coordinate system. We find a collection of parallel vector fields that pair to 1 and 0, and then we compute the Hamiltonian functions.
So this is a Taylor space. Is there some geometric description of this?
Yes. Well, the geometric description is not as clean as Tengren space, I guess. But I think of them as, I mean, in the proof of theorem 2, in fact, what you have to do is you need to, I mean, how to say this? When we build the double coordinate system, the vector fields we use to construct this have a lot of geometric meaning, okay, which I can explain to you later, maybe. And then I just interpret the Hamiltonian functions as, well, conserved quantities of these flows.
Naively, it seems like what you're doing is just trying to describe in some combinatorial way. It's nice all of the ways to change it.
Exactly, that's what you need to do.
Does it matter that it's a Hitchin representation?
So that's a great question, right? So at least the formalism I use here, you need to be Hitchin, because in order for me to make these matrices make sense, right, I need like the correct transversality properties of the Ferny curve. Okay, and in fact, if you can show that if you want all of these matrices to make sense, it forces your curve to be Ferny. Okay, but it's a good question. Like for example, if you want to try to do this for the, let's say for the space of maximal representations, right? I think if you have a good global, if you at every point you have a good description of all the possible ways you can deform the curve, then you can maybe try to do the same idea, right? You combinatorially describe all the possible ways you can deform your triples and quadruples of flags, and then you can do something like this as well. But yeah.
I have a question too. Is that, for example, you always has a function one.
Yes.
You use a function locus
Yeah, so yeah, I haven't really thought about that question, but yeah, I'm not sure. Yes. Yeah, yeah, you can. In fact, that's what we do in the paper. Oh, and SL2? Yeah, so in that case, it depends, right? So it really, what the deformations you do, it really heavily depend on your triangulation. But if you choose, let's say, the triangulation that comes from a Pence decomposition, then exactly what you're doing is you're doing shearing along the closed edges, and then you have some flows that we can describe that changes the length, right? And that's where you get the Fenton-Nielsen coordinates from. Well, it's not an earthquake because I know there's no measure involved. Yeah. But that's a good point, right? You can try to ask if you can try to do something like this for a more general lamination instead of a finite ID triangulation. And the problem here is that I don't know how to do the analysis of what happens when you cross uncountably many edges. Right? The thing about here that's nice is that the only place where everything is locally infinite is about the closed edge. And so if I analyze and understand that well enough, I can do everything. Right? But for general lamination, I don't know how to do it.
The edge, the edges, just related to some length function.
Yeah, so it's a linear, it turns out it's going to be a linear combination of length functions. Yeah.
Are there any other questions? Thank you again.